Transport Phenomena in Biosystem Module 2 Conservation and Momentum Segment 1 Fluid Kinematics with me Yusuf from Institut Teknologi Bandung. In this module we will discuss about fluid kinematics, conservation relations, fluid statics, constitutive relations, laminar and turbulent flow as well as application of momentum balances. Fluid kinematics refer to fluid motion in time and space. When describing motion, we must specify a frame of reference. One choice is to use a fixed reference frame and to examine motion relative to this coordinate system. Alternatively, the reference frame can move at some speed and all motion is relative to the moving reference frame. For the most part, we use a fixed reference frame, although occasionally the solution of some problems becomes mathematically easier with two moving reference frames. Observing motion from a fixed reference frame is referred to as an Eulerian description and is a common reference frame for fluid mechanics. An alternative approach is called Lagrangian, where one follows all fluid particles and describes the variations around each fluid particles along its trajectory. For the most part, the Eulerian approach is used to develop and apply conservation equations for mass and momentum. The Lagrangian approach is used to examine the motion of proteins and cells in a fluid. Control volume is a convenient region of space and it is used for purposes of examining the flow of mass, momentum, and energy as shown in the figure. The specification of a control volume is arbitrary to make the analysis and solution of a problem much easier. Control volumes can be fixed in size or may change size with time. Further, control volumes may be fixed in space or move with some arbitrary velocity. In general, the control volume has a volume Vt and a surface St. A unit normal vector n is defined at each point ds on the surface of the control volume. This vector is extremely useful in calculating velocities and stresses. The Eulerian view examines the control volume from a fixed reference frame. In contrast, the Lagrangian view associates the control volume with a specific mass of fluid and follows the mass as it moves through the flow field. Velocity field. Knowing the fluid velocity as a function of position and time enables one to calculate forces and stresses. Again, the frame of reference used to define velocity must be carefully specified. Motion of a differential fluid element using a Lagrangian approach is shown in the left figure. At time t, the particle is at position r, which has coordinate x1, y1, and z1. At time t plus delta t, the particle has moved to r plus delta r with coordinates x2, y2, and z2. The velocity of a fluid element is the rate of change of the position of the fluid element with respect to time. Velocity has a direction and a magnitude and is therefore a vector quantity. For a rectangular coordinate system, the velocity can be expressed by equation 1. Motion of fluid through a control volume using an Eulerian approach is shown in the right figure. Let's consider a differentiable cubic control volume fixed in space with origin at x, y, and z as shown in the right figure. At a given instant in time, fluid elements enter the volume with one velocity and leave with another velocity. Velocity is a function of location and time. For mixtures, the local fluid velocity is defined in terms of either the mass average velocity or the molar average velocity as shown in equation 2. Flow rate. When the velocity is known, the average velocity and the flow rate can be determined. The average velocity is the integral of the velocity that passes through a reference area divided by the cross-sectional area as shown in the right figure and can be calculated using equation 3. The average normal velocity is also referred as The volumetric flux of fluid. The flow rate characterizes the amount of fluid that crosses unit area of the flow field. The volumetric flow rate can be calculated using equation 4. The mass flow rate is the integral of the product of the local density and the velocity and can be calculated using equation 5. Acceleration is a vector defined as the rate of change of velocity. Fluid acceleration occurs when the velocity changes with time or space. The total derivative of the velocity can be obtained by applying equation 6. The acceleration of a fluid element thus has two terms. The first term on the right-hand side of the equation 6 arises from the instantaneous change in velocity with time. This term is referred as the local acceleration. The second term is unique to fluid elements and represents fluid acceleration that arises from a partial change in the velocity field. This term is called convective acceleration. Streamlines and streaklines. Once the velocity field is known, there are several ways to display the information. One approach is to show the velocity vectors as arrows as shown in the left figure. In this example, the size of the vector is proportional to the magnitude of the velocity. The method of display works well for one-dimensional flows and some simple two-dimensional flows. For complex flows, line can display a curve that is everywhere tangent to the instantaneous velocity vectors as shown in the middle figure, which is also known as a streamline. For steady flow, a fluid element moves along streamlines. Since the streamlines are always tangent to the velocity vector, there is no flow normal to the streamline. This result is very useful in developing control volumes to analyze complex flows. The velocity components to differential changes in position of the streamlines can be expressed by using equation 7. Numerous techniques are available to visualize fluid flows. Some visualization techniques trace path lines if the motion of an individual particle is followed, or straight lines if a continuous path is examined. Path line can be produced by injecting individual bubbles or dye for a brief interval, whereas straight lines are produced by the continuous injection of a dye at one location. Both path lines and straight lines represent the trajectories of particles or particle paths. For the next segment, we will discuss about conservation relations and boundary conditions. Until then, I am Yusuf from Institut Teknologi Bandung.